This is the screencast for section 2.5, example 2, complex conjugate zeros. Okay, so we've got these imaginary zeros that we're now being introduced to that qualify as zeros in a polynomial, but are not places where the graph will cross the x-axis. Well, these imaginary zeros are all of a sudden apparent to us because you don't usually see them in a polynomial function. Well, that's because complex zeros come in complex conjugate form. So in other words, if you have a plus bi as a complex or imaginary zero, you will have a minus bi also as a zero. And the reason why imaginary zeros always come in complex conjugate form is because when you multiply them out, then the i's will always disappear. Complex conjugates, when you multiply them out, the i's will always disappear. If that doesn't happen, then you know you did something wrong. That's also why in the last screencast I gave you the hint of multiplying the i's together first. So an example of a complex conjugate would be if I have 3 minus 4i, 3 plus 4i would be its complex conjugate. Or if I had, let's just say 2i, its complex conjugate would be negative 2i. So the I term changes signs. Let's look at example 2. Write a polynomial function of minimum degree. Minimum degree means don't make up any more zeros than really need to be there. Just limit it to the zeros they give you. In standard form, so that means we got to multiply all this out. Wonderful. With real coefficients, so that means we should not see any i's in this function at all. So here's the function, y equals, if negative 3 is a 0, that means x plus 3 is a factor. If positive 4 is a 0, x minus 4 is a factor. So in other words, the zeros get plugged into x minus the 0. X minus negative 3, x minus 4. This one will be x minus 2 minus I. Remember to put the 2 minus I in its own set of parentheses so the negative sign gets distributed. But also, we're forgetting about a 0. I said that imaginary zeros always come in complex conjugate form. So that means this, the instructions here did not give you all of the zeros. There is 2 plus I that's also a 0. So x minus 2 plus I. So multiplying these first two terms together is pretty easy. So that would be x squared minus x minus 12. Now these guys, I'm going to first distribute the negatives, so this is a little easier to work with. X minus 2 plus I, and then x minus 2 minus I. Now I can take, and remember still, the trick holds true, multiply the I pieces together first. So I have x times x is x squared. X times negative 2 is negative 2x. X times negative I is negative ix. Now moving on to the negative 2. Negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4. Negative 2 times negative I is positive 2i. Now the last term, I'm going to multiply by I by everything. So plus ix minus 2i, and then at the very end here minus I squared, which we know is negative 1. So I'm going to simplify down this mess first before I start multiplying like crazy again. So I've got an x squared. Let's see, I have a minus 2x and another minus 2x, which gives me a minus 4x. Now this negative ix and positive ix go away. That's because we multiplied complex conjugates together. Remember? 2 minus I, 2 plus I. Then, let's see, again, positive 2i and minus 2i disappear because of complex conjugates. Now I have this 4 that's left and a minus I squared. Well, I squared is negative 1, so this is really minus negative 1, which is a plus 1. So I have 4 plus 1, which is 5. Now I get to multiply these trinomials together. X squared times x squared is x to the fourth. I don't need parentheses anymore because this is the last multiplication I'll do. X squared times negative 4x is minus 4x cubed. X squared times 5 is plus 5x squared. Moving on to the x, negative x times x squared is minus x cubed. Negative x times negative 4x is positive 4x squared. Negative x times 5 is negative 5x. Negative 12 times x squared is minus 12x squared. Negative 12 times negative 4x is positive 48x. Negative 12 times positive 5 is minus 60. So I'm going to simplify, and then I'm definitely going to graph and check this. So now in y equals, I put the very, very last thing written by myself. I want to check my answer all the way to the end. So I put this down, put this in y1, my last step. I'm looking for, on my graph, I should see the function cross through negative 3 and positive 4 on the x-axis, but it's also quartic because there are 2 more zeros. So I'm looking for only a cross through at negative 3 and 4. The function should touch the x-axis, nowhere else. So let's see. Yep, negative 3 and positive 4 is where the function crosses. Both end behaviors go up to positive infinity because it's a quartic, an even degree polynomial. And I have this change from decreasing to increasing to decreasing to increasing that kind of symbolizes this is more than a parabola, so a quartic would make sense in this case. So it looks like I did this problem correctly. The now try problem is number 7. Write a polynomial function of minimum degree in standard form, bummer, with real coefficients whose zeros include those listed. Okay, so polynomial function with minimum degree. So I have zeros of 1, 3i, and negative 3i. Oh, look, they gave you both of them this time. Good. But I don't need to make up other zeros. I'm not going to make 5 and 0 and 87. I mean, let's just use what we're given, and that's it. Minimum degree. In standard form does mean that I need to multiply all this out. So first, y equals, if 1 is a 0, x minus 1 is a factor. Because if I plug in 1, it has to make it 0. If 3i is a 0, x minus 3i is a factor. If negative 3i is a 0, x minus negative 3i, which would be then x plus 3i, is also a factor. So I got to put this in standard form. I'm going to multiply the I terms together first. When I multiply the I terms together, I got x squared minus 9i squared, and then changed the I squared to a negative 1, which made it x squared plus 9. Now I can FOIL out this last step. And the directions said I had to write it in standard form. This is not in standard form. I have to make sure that each exponent of x is decreasing. So this will be x squared, x cubed minus x squared plus 9x minus 9. So it goes 3, 2, 1, and then 0. And of course, I'm going to graph this and make sure that the graph only crosses the x-axis at x equals 1, and it looks like a cubic function because I have 3 separate zeros. So I've graphed my polynomial, and I can see that the graph does look cubic. It's got a curvature in there, so it is not linear. It's got opposite end behaviors, and it also only crosses through the x-axis at x equals 1. So it lines up with what my algebra said it was going to do.